to welcome everybody to this last OLOFOS seminar before the May workshop. We are receiving someone that came here many years ago, in fact, that is back, till Grüne-Yanoff, who will talk to us about modalities in modeling a separate scientific practice, and you have the floor.
Thank you, Alexander. It's a great pleasure to be here again. I particularly enjoyed this occasion because I thought I wasn't entirely sure how close interests are. So this is a bit of a, I tried in any way to sort of take a little bit of a step back and try to sort of give a bit of an overview of sort of the broader research interest that I have. Maybe start by giving you a little bit of background so that you understand where I'm coming from. I work in philosophy of science and decision theory. I have a background in economics, and I collaborate quite a lot with psychologists and behavioral scientists. So I sort of do empirical work, experiments, but this is not what this concerns. One of my earlier works coming from decision theory, formal decision theory, was my interest in how social scientists use formalism or sort of mathematical models, mathematical formalisms to for their work. So how can you learn something from models, and how in particular can economists learn from models? So some of you might be familiar with some of the work in economics. Economics has a lot of they call theoretical modeling that is quite separate and I believe works quite differently than as you would use models in physics, so far as that these are often quite freestanding structures that are proposed and then often enough only motivated by some very basic theoretical structure, and otherwise motivated by plausibility considerations. And then the conclusions are quite separate or distant from actual observable phenomena. It used to be in economics that people would sort of work quite separately in the theoretical and the empirical part. And in the theoretical part, they would propose these models. And then the question often was like, okay, so you're proving us rigorously some result here. And for what purpose? Or how is this going to connect? And one answer that was given either explicitly in some other papers or implicitly by modelers was that, well, it shows some kind of possibility. That was sort of about 10, 15 years ago. That sort of like what I took as a starting point, wondering, what does that mean? Am I supposed to take that seriously? Like, is that a real scientific result, or is this more like a fig leaf and a very thin one at that allows people to say, well, I get some result, and that is supposed to justify what I'm doing. So out of this, and that was sort of the starting question of the relation between models and modality and sort of possibility. More generally. Since then, I've been writing, I've written a number of papers. I ran a research project, and we currently that has just recently finished, and that I now want to expand, where a focus has been on what is known as philosophy, science, and practice. Those from my reading are two this particular kind of philosophy of science that characterized by two principles. The one is that it really tries to focus on actual scientific practices. So it's important to, instead of now replicate the economists and their sort of grand theorizing about doing it in philosophy, to try to first start out with documentation of actual practices found in different scientific disciplines. And then the second principle is that the analysis and the results should in some way also affect or have some relevance for science. So the typical way I'm thinking of that is that I'm trying to formulate, or I'm aiming to formulate methodological principles. So questions regarding method choice, justification of method choice, criticism of methods that have been applied in a way that interacts with scientists. And that's sort of the broad context in which this work happens, and then I hope that I fit today's talk in as well. Now specifically I'm talking about modal modeling as a separate practice in science. Right? It's quite broad, so let me explain what I have in mind here. So modality can refer to a lot of things. What I'm largely focusing on here is actually specifically possibility and necessity. I think this can and it should be expanded to include also counterfactuals, dispositions, and so on, but it's that kind of more specific modality that I have in mind. Of course, there are other, philosophers use modality sometimes broader than that, but those other aspects, those other modal modalities I will not discuss. And by scientific modeling practices, I mean the use of artifacts, which can be, of course, objects, sort of material objects found in some way, but then repurposed for representational, sort of as representational vehicles for epistemic purposes. And the big idea behind this, I'll discuss this more later, is the idea of surrogacy. So we're taking an artifact that stands and we're studying that artifact because we claim that it stands in for something else. So we're not, instead of studying that thing itself in some way, we're studying this thing that the surrogate that stands in its stead. And by modal modeling practices, I mean specifically those practices that are employed in order to infer modal claims. And here, the examples you'll see are almost exclusively focused on claims about possibilities, even though they sometimes can be relevant for claims of necessity. That's what this is about. And what the argument that I want to make is quite broad, but I think nevertheless is important. Important also for me because I've made this claim in sort of defending or proposing research projects of saying that, well, modal modeling is a particular kind of scientific modeling, and that requires a separate treatment due to conceptual, epistemic, and methodological reasons. It's special in some regards, and in particular, it cannot be properly analyzed, nor can there be proper relevant recommendations be made based on the standard account or standard accounts of scientific modeling. So the point here is that philosophers of science, I think, have spent a lot of time focusing on scientific modeling and have actually done what I think is substantial progress to understand how scientists use models and how we can at all learn from models, given that they abstract and idealize. But that this standard account, which I will characterize later in this talk, is not really suitable to help us with understanding and improving modal modeling practice. Yes?
Just a small question for clarification. I assume, given that you make this distinction, that you don't count causality as a modal notion, given that that would be traditional modeling.
Yeah, actually this is a wonderful and difficult question. I would not want to, given that many accounts of causality involve counterfactuals, and it therefore will involve some form of modeling of non-actual possible states or events that and therefore might fall partly into the category of modal modeling. Yeah? I know that gets me in hot water because it expands drastically the domain of modal modeling, right? So modal modeling is not some kind of tiny marginal thing that's happening somewhere. Modal modeling is happening and might actually be happening in a lot of modeling, but I don't think that we actually have very good answers currently to address these things. To address some of the issues that I'll bring out here and that apply to questions of modeling counterfactuals. So that's but I should also say that's a bit of a hot potato that I try not to make in my work so far. I make a sort of central topic. So I've been sort of skirting around this, and it's partly this talk where I try to address this. So I'll proceed as follows. I'll start by giving you a number of examples from different disciplines where I think that illustrate sort of a diverse set of modal modeling cases. I'll then identify, despite all this diversity, what I think are the important unifying features. This is sort of a bit of a no, sorry, that's a sketch. And then I'll remind you of the standard account of scientific modeling, which in itself also has to be a sketch because, of course, as you're aware, in philosophy there's nothing that sort of is this consensus opinion, but I think I can point out sort of that there are core features that are largely consensus and that will stand against these relevant features that I've identified, and then explicitly contrast modal modeling in three regards, 3 dimensions with the standard account, and then conclude from that that modal modeling should be a separate kind. So let's start by looking at some modal modeling illustrations. So let's start with synthetic biology. About 20 years ago, chemists and biochemists have started to synthesize substances that are quite close to DNA. So on the left here, what you see is one of the building blocks of DNA, adenine, however, expanded by a benzene ring in the middle. So the left and the right rings are the same as an adenine, but now there's a benzene ring in the middle that expands this, and that's why they call it X-adenine. And X-adenine, interestingly, interacts with the other building blocks that of DNA, so that you can combine that and build the double helix of DNA in a similar way that is as standard or DNA, something called bDNA. It's actually energetically a little bit more stable than DNA. It's also a little bit larger, and it can codify more information than standard DNA can. And then this Hachimochi DNA is a further development that's newer, that sort of actually expands the potential of informational content even further. There are lots of purposes for this. These are not, of course, there's some models involved, but here these are real, actual substances that were synthesized. Some of the purposes concern, like, okay, we might use this stuff to actually for information storage in the future, so a completely different, not silicon-based, but DNA-based work. But what is of interest here is that it becomes quite clear in that some of the researchers are also excited about is that, this DNA-like, these DNA-like substances meet sort of like the main requirements that are needed to support evolutionary dynamics, in particular information conveying information as DNA does, so that it could function as a replacement of DNA in organisms. And therefore, they conclude here, for example, in the paper that presented the Hachimochi DNA, that these results expand the scope of molecular structures that might support life, including life throughout the cosmos. And so what happens here is that now we're thinking about models of organisms that don't, for all we know, exist or that we don't know anything about, whose genetic information is encoded not through DNA but through some of these expanded or modified DNA structures. And the one question that this answers, for example, is DNA necessary for life? And their answer is no. It's possible that life could have evolved with those structures instead. It would look maybe slightly different. For example, there's more information that could be included in a single cell. There are different stability conditions. So we can answer that it's not necessary that DNA isn't necessary for life. Life could have on Earth evolved differently, and potentially life has evolved elsewhere with these different, based on these different substances. So here we're making very strong possibility claims based partly on the existence of such substances and their properties, but partly also on the representation of possible but non-actual organisms. Here's a second example. Up until, this is from economics, up until about the 1930s, economists believed that the observed periodicity of economic growth, so that there are typical cycles that involve a recession, a depression, and then moments of growth that then are again bent downwards. That they were caused by some underlying cyclical cause. So in the late 19th century, for example, William Javin's theory of sunspots was very popular. Basically the idea that the periodic changes in the sun, transmission of energy to Earth, affects harvests, and that causes a change in economic activity that translates into these cycles that we're seeing. Then there were Marxist analyses that focused more on credit and credit flows and who was given credit and so on within the capitalist system. Instead, a Russian economist, Slutsky, he suggested and this is very explicit in his paper, the possibility that these cyclical movements were produced simply by random shocks that were not in any way cyclical. Well, how did he show that? Well, he used a model, some rudiments of which I can show here, where he produced a sequence of random numbers. And then he ran 10 moving average of these random numbers, and then that generated this. You see here, you see here the random number series and their respective averages, and you can see that this generates some form of cyclical movement. Now, what he then did in the third step is to take British GDP data from the late 19th century and compare. And you see that the the dotted line is what the model produced based on the random numbers, and the continuous line is the actual GDP, and it's actually quite close. So what he showed, or what is widely today accepted, is that it was possible that GDP fluctuations, cyclical fluctuation, happen through such a mechanism, and not through any of the things that have been proposed so far. Now, what is crucial is that he did not show that these were the actual, right? This is a purely theoretical exercise. It's a sort of like, look, we can generate such dynamics, and these dynamics actually match this quite well. So therefore, it's possible. We don't necessarily need to look for a cause that itself has a cyclical property. And that was a big step then gave rise to what is now known as the random shock theory of business cycles. That was then, and since then, of course, this has been much more supported by evidence. So today we wouldn't talk about this as a theoretical possibility. At the time, Slutsky, all he did was to conclude that this was a possibility without any evidence that this was the actual cause. So this is a quite different form of possibility that we're talking about here, yet again generated through models. A third example that I want to share with you concerns climate science. So as most of you will know, in the reports by the International Panel on Climate Change, the one core base for these reports is the workings of many separate modeling groups, each of whom develop a separate general circulation model, GCMs. So which model the climate the atmospheric circulations of the Earth, but they use they often use separate modeling structures that are independent or at least not identical to each other. And then what the IPCC gets and what they synthesize is a sort of what they call an ensemble of models and of model results. And the reports then typically look like in this graph. You have the actual observations as shown in the black line. And then you have the models that make predictions from various points in time. And as you see, of course, unsurprisingly, they expand like a cone. So we have, and one should add to that of course, there are two main factors that here play a role. One is that there are different RCPs. Those are different forcing scenarios. Sorry, these are actually CO2 concentration scenarios. So forcings play a role in that, but it's sort of about, well, we make assumptions how much CO2 will be in the atmosphere at a certain time, and then we're modeling the climate based on this scenario. So there's sort of two possibilities. One is that we don't know what the actual CO2 concentration will be, and then we're putting on top a circulation model that will investigate how the circulation actually plays out. And therefore, you get with certain scenarios. You see here, this is all red. This is a much higher concentration. Regardless, you get considerable differences depending on what model you're using. While here, with a lower concentration, you're still getting a considerable variation. That actually, some of these models, here's one of the blue with a lower concentration, and then down here you still see that there's one red line, so there's even some of the high concentration. So there's substantial spreads. Now, the IPCC has had difficulties interpreting these ensembles. In fact, up to its fourth report, they have treated these as if we should think of them as sort of like something that we can average over. Sort of average predictions have been produced. And there's been a response by climate scientists as well as philosophers, but these all I'm quoting here, these are all climate scientists who say that's rubbish. Yeah, we shouldn't do that. There are lots of reasons to believe why we should not think of these models as something that can go into an expected value calculation. Instead, we should think of each of these models as a possibility. So they're thinking of possibilities for future real-world climate, a range of possible developments, or the spread of possible future climate change. So these are so here we get an explicit interpretation of models, or we get a debate. Not everybody agrees to that. That we should think of these as possibilities rather than point predictions. With, let's say, point predictions with an imprecision, which we then take out by averaging over. Okay, then we move on to engineering science, where we have a proof of concept as a very core of the design process. So engineers design, and a design process crucially involves that you're generating physical systems that you hope will correspond to a set of functions that you require for such a physical system, and if they do, you have developed a new artifact that has both physical and functional properties. So this happened in the development of space rockets. Robert Goddard is one of the early pioneers. In particular, he for the first time thought about developing liquid propellant rocket engines. So before, people would fill rockets over the centuries with black powder or things like that. They're all solid. Here, you're using liquid oxygen and some fuel. At his time, it was either ethanol or petrol, and later on it became then hydrogen. Goddard himself already suggested hydrogen, but was afraid of using it because it's pretty high risk if you don't know whether your tanks actually leak or not. But the important thing is that what he did was he didn't just build a rocket and sort of shoot it into space. Rather, he developed these sort of stationary scaffoldings, and I think he's standing next to one here, where he was just trying to show that such fuel, liquid fuel engines could actually produce the right kind of propellant energy. And he performed this test that was considered successful, and historians have argued that it was a major success for Goddard, this particular sort of static testing of the firing of the engine, because it proved that a liquid fuel rocket was possible. And I think that's a very common and often somewhat overlooked stage in engineering, that engineers produce prototypes, which consists only of sort of very rough approximations. They say this is a prototype of a space rocket, even though of course this thing might not be able to fly at all, or certainly cannot fly into space. And yet it has certain prototype qualities that show that certain bits of it have the possibility to satisfy the function that is desired. And so again, the demonstration of of such a proof of concept shows a possibility. And now a last one from the social sciences that concern the evolution of cooperation. These are often done by defining agents on a lattice. So you see these points here. These are, and then you interpret this lattice as a neighborhood. So people are not when they interact with each other, they only interact with neighbors. And the way they interact typically in such models is by they play as a one-shot prisoner's dilemma. And then you can introduce various degrees of altruism, variously defined. And then you see how much cooperation in these prisoner dilemma games you get. And from that, people have concluded various things. There's a whole literature that's mainly in what's called analytic sociology that make use of these agent-based models. And what is interesting, what I want to show you here, I hope you can read this. This is sort of a partial summary from an overview paper that looks at these simulation studies for cooperation. And in, I would say, about 80 to 90% of all the papers reviewed, the result is always that something can happen. Yeah? So cooperation can evolve, can emerge, it can be sustained. Commitment can be, or trust can select exchange partners, and so on. Yeah? So that was, I thought, was stunning, right? Imagine you read in physics sort of a summary of papers, so like an overview review of a subfield where people say, well, our results were that X can or might happen. That's a contrast here. Right? So then you wonder, okay, is this in which way is this actually relevant? Is this science at all? I mean, are we showing something that is this of interest in the first place? And then if it's of interest, how do we support such claims? Okay, so enough of the case studies. I think what I wanted to show is that they are diverse. They're diverse in their in their subjects, right? Anything from rockets to DNA. But perhaps more importantly, they also differ in the kind of possibilities that they are inferring. So in each case, there is a possibility inferred, but in some cases, we might talk about past possibilities. So as when we say that they could have been, life could have evolved with XDNA. In other cases, it's clear future possibilities. Like in it's possible to build a space rocket with a liquid fuel motor. There are. I'll come back to that later. In many cases, it seems that the possibilities are about something that is in the world, in the sense of that the world is this way. But it could have been different. That's what I call what is typically called an objective possibility. But in some cases, the distinction isn't so clear, and instead the possibility might be about only the actual world. So what is the case, but judging our inference ability. So we might say, well, given our current knowledge, it's possible that the actual world looks like this, or it's possible it looks like that, in which case we're talking about epistemic possibilities. I'll come back to that later and discuss, we can discuss where some of these cases might be ambiguous. They clearly also serve multiple different cognitive functions. So in some cases it's about mapping future uncertainties. In some cases, it might concern understanding. In some cases, it might concern questions of contingency or necessity. In other cases, it's as practical as designing something. And I also think, and that will be a topic that I will discuss more, there are also differences in quality. So in some cases, I think the inferences are quite strong, while in other cases, the inferences seem to be pretty weakly supported. And that's something that I would like to discuss in more detail. But before I do so, let me first try to sort of now focus on what I think are the core aspects of MM, of model modeling. What unifies these obviously very different, diverse examples? So in all these cases, model modeling uses representational artifacts to facilitate inferences of possibilities. So we have what we might call a model, and the model might consist in something physical, like for example the engine that Goddard actually tested, but it might also be something as ephemeral as a particular state of the computer that is then represented in such a lattice or sort of where it might be a mathematical model. And in each of these cases, they're used to draw conclusions about possibilities. Now, but another important feature is that at least in some of these cases, these models seem to have served as central and fundamental scientific functions. So this was not just sort of like some pet project that someone at some point thought was maybe interesting on the side, but this is something that this is a bit of a side remark here, but I still I think it's important to stress that might answer some of the most central questions or most fundamental questions that scientists have or could have. And for that, it may be, so as soon as someone talks about fundamental scientific questions, then should quote Einstein. So here we have a quote which I think is wonderful. It's a little bit shortened, but what he said is that we don't just want to know what nature is, so what the world's actually like, but we want to know why the world is like this, and why it's not different. And why it's not different refers to the other. That's sort of how it possibly could have been, but isn't. Or there must be some form of identification and possibly representation of how this different could have been. In a similar way, Ronald Fisher, the biologist, very much pushes this when he talks about, this is a book about the biology of sex, and he's interested in sexual reproduction, and he says right in the introduction, well, obviously biologists are not going to now start investigating sexual reproduction where there are 3 or more sexes involved, because he thought there was no. So all he thought, which might be wrong, that all organisms only come in maximally 2 sexes. There are no reproductive systems that have 3 or more. And therefore he thought, intuitively, biologists of course would say, nobody wants to study 3 or more sex reproductive systems. And then he says, however, what else should we do if we wish to understand why the sexes are in fact always 2? So this corresponds, I think, very nicely to Einstein's idea. So it's like, well, we don't just want to describe everything in the world just happens to have a 2-sex reproductive system, but instead what we want to know is why is that? And that requires, Fisher is here more explicit than Einstein, that we actually need to investigate how a 3-sex system would look like, or as he says, how would the consequences of such a 3-sex system be experienced by an organism? By which I think we can assume he means that we need to model it. So the point here is that sort of here are some of the deepest and most interesting questions that scientists can pose. Right? It's about understanding, it's about giving complete explanation why things are the way they are, and they require the reference to modal inferences, and some of these calls, even in the 1930s, 20s and 30s, directly refer to models. But I add, they might or they can serve such functions, but others might not. So that's also therefore an important issue about the quality. So, and here we now need to take a little step back, think about, well, what are modal claims or possibility claims? Well, whether something is possible or necessary is a matter of fact. It's not just a matter of something that you could just decide subjectively, or that is random or something. But indeed, we can assign and do regularly assign truth values to possibility claims. If we do that, then it's also clear that inferences to such possibility claims differ in their degree of fallibility. Some of these inferences might reliably lead to true conclusions, while others might not. And therefore we need to assess the quality of such tools of inferences, and the question is how. In addition to the quality question, we also have, I'll work out that out later, an issue of relevance. And that's actually something that will be the second big question. So the issue here that I want to discuss is, well, how should we determine the quality and relevance of multiple modeling instances? So specific cases of multiple modeling. For that, let me take a step back and let's look at the standard account modeling. Perhaps one could say, well, that's what just expand the standard account to include also these kinds of model applications, and then maybe that helps us to answer these questions, how to do that. So the standard account starts with the idea of surrogacy. The fundamental role of models is to stand in for targets, for their targets. They stand in for something else, and that's something else that we call a target. And then we might generate predictions about the surrogate, or we try to manipulate, observe, modify, analyze these surrogates, but with the purpose of learning about what they stand in for. And importantly, in the literature, what these models stand in for is actual targets. So there's a fair amount of discussion about the issue of targetless models. So they say, well, what happens if you have a model, if you sort of have, let's say, you have a painting of a unicorn. We know unicorns don't exist, so now that's not a scientific model, but it's a representation. So is it a representation of a unicorn? Well, unicorns don't exist, so how could it be a representation of something? It doesn't have a target. It's a targetless representation, and that's a bit of a difficult thing. And we have then analog cases in science where we might have models that are targetless. This also indicates that, well, that the main focus of the standard account is the actual targets, not non-actual targets. You had a question?
No, it was not a question.
Oh, okay. Yeah. That also means that models can misrepresent important things. That sort of is not the standard account acknowledges that there is an intentional aspect in modeling. So we declare a model. I might declare something to be a representation of something else. But then the question, and we cannot then deny that. So we can't say, no, it's not a representation. But we can say, well, it's a bad representation. So that's not simply a matter of stipulation, but rather once it has been declared that this is supposed to, in the following way, represent these features of the target, then we need to debate whether it does so well enough. And this well enough is something that, even though the well enough is mediated by purposes, so we often talk about adequacy of a model, that all the literature on adequacy concerns what the actual standards of accuracy should be, but ultimately it nevertheless boils down to accuracy. Yeah, so we acknowledge that models abstract and idealize and make assumptions about the target that are clearly not true in one regard or another, and then we say, but it's nevertheless adequate because these idealizations don't affect whatever the role of or the function of the model for this purpose is supposed to be. Now, that's the good argument. But that means that, well, in some way, it still has to be an accurate enough representation of the target so that the quality assessment is dependent on the relationship of target and model. And that is then measured either by similarity, resemblance, isomorphism, or what have you. But some form of target model comparison is used here. These models clearly have important functions. There's been a lot of, I think, successful arguments to show that despite their abstracting and idealizing nature, models can provide explanations, they can predict, and they can lead to design success. Therefore, a typical understanding of modeling practices and of progress in the modeling practices is that you develop a model, and then you either modify that model in order to make it more adequate, or you replace it with a newer model, thus discarding the earlier model, at least for that purpose. And that's what sometimes is called vertical progress, that sort of displacement. We're sort of always aiming for the most adequate model. That's the one we want, and the rest can go away. Okay, I'll get stuck here. Why is this happening? Here we go. So let me summarize these in three dimensions. You see that here I have about so I can draw certain things together. I'll first talk about along the three dimensions that I want to contrast with the actual account, the standard account with the multiple modeling account is surrogacy and target actualism, representation of quality and accuracy standards, and third, cognitive functions and vertical progress. And here, most of my research work in one way or another comes in, but I'll try to keep that brief. I don't want to go into detail, and we can do that in the discussion instead. So when we talk about surrogacy, there's a big discussion. What modal modeling actually has as a target? And a common, partly because it's an early proposal, has been to think of these multiple models as what Michael Weisberg called hypothetical models. And the idea is that hypothetical models represent possible targets. And then he very quickly says, oh, but that's metaphysically really gnarly, so let me not get into this here. But that's been a very popular proposal to think of, well, okay, so like you have a model of this building, like it actually exists, and then maybe the architect, upon his, when in the planning phase, proposed 3 different kinds of design for these buildings. 2 were not built. Well, that represented a possibility in some way. And sort of, then you have to think about what is the status of a non-built building, right? But in some way, I think it makes sense. It corresponds to some of the cases that I think this guy discussed. That sort of we might think of these ex-DNA-based organisms as, or models of these as representing such possible organisms, or of Slutsky's possible cause of the business cycle. Another option is to say, no, these models are targetless. They don't have targets at all. But targetless models, nevertheless we can analyze. And here the Roman Frigg and Jameson Guyon's Dickey account is helpful. Some of you might have heard of this, where they say, well, a model becomes a model the moment that we give it an interpretation. So think of this in the first place is just a grid. That's just a grid, a very fine grid that has a certain dimension and a certain extension, but we can interpret this as a neighborhood. So we interpret some of its features, namely that the adjacency of cells, we might interpret as being a direct neighbor to, and that in turn means that the inhabitants of cells, which we interpret as agents, they can interact with their neighbors. And at that moment, we already have a model. But it might turn out that there is no such neighborhood. So it's targetless in the sense that that no such neighborhood exists. The model therefore cannot represent it. It cannot refer or denote that particular neighborhood as it doesn't exist. However, we can nevertheless say, well, it's a kind of neighborhood. We all have an idea of what we mean by neighborhoods. This particular neighborhood doesn't exist, because all neighborhoods are not, no singular neighborhood has always 4 neighbors, let's say, and therefore, but we can nevertheless expand from actual neighborhoods. We understand being adjacent and interacting with each other, and therefore we can think of this as a neighborhood model, even though it doesn't have a target. That might help in some way. Or a third option is to claim that no, actually, modal models have actual targets. And here, so it's Peter Tan, who some years ago sort of just recently proposed that the targets even of these hypothetical models are actual systems. And then James Nguyen has proposed that at least some of these models represent actual targets, including their dispositions. And this might make sense if you think of, for example, I think most clearly this makes sense in the case of the climate models. You might say, well, it's the current climate system that has certain dispositions, right? And now we're thinking about, at least in terms of the different concentration scenarios, how these dispositions actually play out in the future. And then maybe there's some uncertainty here about this. So these dispositions could play out. There's only one set of dispositions and we don't know about this. So here you have a very clearly then an epistemic possibility interpretation. But we're attributing, the only target is the actual current climate system, and we're trying to now figure out how the dispositions, when they realize, in which direction will they carry this system. All right, so that's the first issue that arises, right? That's with respect to surrogacy. How can we accommodate modal models with respect in the standard account if we have issues with if we ask what sort of targets? Because one issue that arises here is that, well, while in this case maybe it makes sense to talk about the dispositions of the climate system, how, for example, would this work with respect to ex-DNA organisms? Are we representing if we have a model of an ex-DNA organism, something that developed with ex-DNA instead of DNA, are we then representing, let's say, an actual mouse that has the disposition that it could have evolved with ex-DNA instead of DNA? That seems very far-fetched, right? Because you might now think, wait a minute, I mean, this might not look like a mouse at all, and we might probably the whole Earth biology would have developed in different ways, And mice wouldn't have developed in this way. So to focus on particular organisms and attribute the dispositions to them seems to be odd. Instead, maybe we have to focus on the ancestral organism, but of course we don't know what that is. Or we have to maybe focus much more broadly on sort of Earth, on the life system on Earth and its disposition. So this is where I think this proposal that would be, of course, the one that sort of accommodates MM in the standard account more easily, has a lot of unanswered questions. Okay, second step is the question of accuracy standards, and here we need to distinguish between objective possibilities and epistemic possibilities. In objective possibilities, it's clear that for hypothetical or targetless models, so the first two answers to the first question, we cannot at all use the standard account of target-dependent model assessment. There is simply no target that we can compare to the model. Or there's a possible target, but a possible target doesn't give us the possibility of comparing the model to its target in terms of similarity, resemblance, isomorphism, and so on. Yeah? So we don't have a handle how to assess this here. When it comes to kind representations, think of the Deki model. Think of that sort of like, it's a neighborhood representation, right? You might say, okay, so was this a reasonably good part of the kind of a neighborhood representation or not? But again, who is determining the kind, and how can we draw an assessment here? A totally unanswered question in my regard. And when it comes to trying to assess these multiple models as actual targets, I think we have a real problem to determine how a model is similar to a target in terms of its dispositions. We have indeed conceptually in philosophy discussed a lot about what dispositions are, how we can interpret them, how we could possibly find out about them. But as I pointed out already, there's this additional question of identification that makes it really difficult. Alternatively, we might think about other justificatory strategies. And here, my collaborator Ylva Krölin-Welling and I have mapped out a number of justificatory strategies that do not depend on a target model relationship. So here we're thinking about, we're drawing on model epistemology justification, for example, imagination. So I'm not going. This is very roughly canvassed, but the basic idea is that if we're able to conceive of something, that might be evidence for it being a possibility. The counter argument is that, wait a moment, we seem to be able to conceive of a lot of things that are impossible. How can we control that? An alternative might be to refer to background theory, so to constrain if we have laws of nature available, if we have true generalizations available that cover the possibilities in question, we might refer to those. Or a particular form of similarity that is closer to this question of kind representations, where we're not comparing model and target, but rather model and some other instances of the same kind as the possibility. Yeah? So we're doing an indirect similarity. And then there's the issue of epistemic possibility, how to evaluate that. In a different paper with Ylva, where we argue that the epistemic possibility, according to the standard account, means you have to see that you have to show that a model is compatible with current knowledge, so this again is not typically captured through the question of a model-target relationship. And then there's the further issue that we are that this is a really weird kind of practical. This concept is weird for practical applications because you're in fact justifying by ignorance. So you're saying you have the more you can justify that something is an epistemic possibility if you lack knowledge that it's not so. And that seems to be an odd notion that sort of does not fit very well with our view about justification. Okay, let's come to the last contrast. And that concerns the cognitive functions and progress. I think it's obvious that modal modeling, to the extent that it infers possibilities, cannot provide point predictions, full explanations of actual phenomena, or design validation. Now, for that, we need to actually have representations of actual phenomena, of actual targets. As long as we're aiming for an explanation of an actual phenomenon, we need to have some kind of representation of that. That does not mean that modal modeling does not have important cognitive functions. And I hope you've seen in the examples and in some of the analysis that I've given you that that modal modeling can provide you with mapping of possibilities or uncertainties. It can provide you with how possibly explanations. It can provide you with the contradiction of necessity claims, as for example in the claim that DNA wasn't necessary for the evolution of life. And it can also contribute to understanding insofar as we want to maintain that understanding requires explanation, but that understanding can, for example, be expanded by questions of contingency or necessity that are not covered by the standard explanation or standard full explanation. These functions, however, very much involve something very different than the standard vertical progress that I mentioned for the standard account. Instead of now providing one model that's better than the previous model, more adequate, what you now do is you're actually proliferating models. You're generating more models that represent possibilities, all of which are supposed to be considered simultaneously. So you're thinking about, if you map possibilities, for example, think of the idea of the climate modeling, for example. You want these models to want to consider these models at the same time, next to each other. You don't want one model, you want many models. And that creates its own problems. In the first place, it generates, if they have cognitive functions at all, then progress now works differently. It does not work vertically, but by expanding the number of models you're considering at one given time. That's what another collaborator, Caterina Marchioni, and I have called horizontal progress. Horizontal progress, however, has its own methodological challenges. The first one is that you can easily proliferate beyond what is cognitively manageable. And then you need to have some sort of somehow need to keep constraints there the right way. And the proliferation can easily be abused and is abused. We know that it's abused. So one is more inter-scientific that we've called, that was with my collaborator Tarja Knutela and I have called the apologetic function of modal modeling. So I think in some of the cases I indicated of the analytic sociology, where you might end up, or maybe in the case that I initially discussed, it was sort of mentioned as a motivator, that seeing that economists or sometimes say, well, it's possible. We're showing that this is a possibility, even though it was unclear that this possibility was in any way relevant or was showing anything that we didn't believe before. So the question is there any novelty in this at all? Maybe not. Maybe it is only a way of saying, well, my modeling activity yielded a result, and that's this possibility, take it or leave it if you don't like it. That's, I think, most intra-scientific. It sort of concerns to assess the contribution of individual scientific projects. But then I think there's a much bigger problem, and that concerns how science is used in a policy and in a political context. So we now have highly professionalized strategies to undermine scientific claims by sowing doubt. This is often called the tobacco industry strategies, because the tobacco industry maybe was the one that most successfully used this for many decades, when it was known that tobacco was causing cancer, and they kept pointing out that it wasn't necessarily so, or possibly it could have been some other cause. This was a very typical way, and so you can see how, in contrast to the examples that I gave you here, that providing more how possibly explanations is a nice strategy to pull the rug from under those who are saying this is the explanation for why the X or Y happens. And to say, well, have you considered that alternative? This could possibly also be a cause. And this is what sometimes is called the agnotological use, the use for making things uncertain. And this is something that specifically happens in those areas where we are dealing with horizontal progress, where we are dealing with proliferation. The agnotological problem does not arise in a moment where we are used to always replace one claim or one model with a better one, and then the question is always, well, which one is the better one? It arises where we allow for multiple models to exist simultaneously, all of which are supposed to fall into the conclusions. And this can give, I think, very important and very negative results for science. All right, so I kept you a little longer than I promised. Sorry for that. But I'm done now. So what I've argued is that from other scientific models, as described by the standard account, multiple modal modeling differs conceptually in their surrogacy and their targets, epistemically in their justification of inferences from these models, and methodologically in the functions that they serve and the issues that arise with them. And therefore, I propose that we need to treat in philosophy of science modal modeling as a separate kind with separate conceptual, epistemic, and methodological resources. Thank you.
So, as usual, let's take 5 before the question period. Do you want a coffee?
I love some.
Question, comments? Daniele?
Yeah, first of all, thank you very much for your talk. I was just wondering, can we imagine to bypass the problems posed by actualism through possible word semantics? I mean, can we imagine that modern models represent actual systems in possible words? What would be the pros and cons of such a perspective? Is this a road that has been explored? Or thank you.
Yeah, thank you. So the possible word semantics is a way of providing a semantics for modal claims, but I don't think it helps us epistemically or methodologically with the problems that I addressed here, because the standard, even a Lewisian realist, which might only be Lewis, but anyway, would insist that, well, you don't have access to other possible words, right? It's not, and so even though we can theorize about them, we have no physical or epistemic access to them. And therefore to say that, it represents a possibility in the sense that it represents an actuality in another possible world is just to push the problem further on. Because then, that means the same problems then arise. That I cannot access it, I cannot compare it. To be honest, I've just manifolded the metaphysical problems, right? Given the issue of possible realism and stuff like that, and it's unclear how this would help any of the issues that arise here in particular, of which I distinguish three aspects. The first aspect is much more like a conceptual clarification, and then there are two practical questions. So one is the assessment of the quality, and the other one is the assessment of relevance. Neither of which I think are solved by the possible word semantic view. Well, that's that.
Thank you.
You're welcome.
Other questions or comments? Peter, I suppose, Mr. Modality.
I have quite a number of questions, but I'll start with great talk, by the way, and I fully agree with it, I think. But just a more like specific thing in the climate models you were talking about. So I was wondering what the difference really is that these critics have seen between a possible future, which was what they were saying such models were standing for, and something that you could use to give you expected values. I mean, isn't that what an expected value basically is? Just like you take the average among possible futures?
Yeah. So I think the easiest answer here is to appeal to maybe where we have a better understanding in the distinction between objective and epistemic probabilities, right? So we are, if you think about the justifications for making use of weighted means, probability weighted means for, let's say, for example, for a decision. Typically, what you appeal to is epistemic probabilities, right? So you're saying, I have uncertainty about how the one world in which I'm making a decision is, and therefore I'm representing that through multiple possibilities that I assign different weights to, and that's a convenient way of accumulating evidence for all the knowledge I have, and then at various times when I need to have action guidance, I'm I'm checking I'm calculating the weighted mean, and that gives me then, in comparison to other sort of, for example, causes of action, gives me sort of an idea of what I should do. Right? And this, but that commits you to, I think, the kind of epistemic position, right? There are, and the question is, can this be applied to, or can such a justification be applied to an objective probability, sort of, in this case, to objective possibilities? If these really are different possibilities, are you supposed to now, why are you forming even an average over them? Because the average was a way, in a way, the simpler way of the way the average here is used is basically to say it's a precision problem. Yeah? It's a measurement error yielding imprecise results. And how do we deal with precision? Well, we average over. We repeat and average over it, and that reduces imprecision. But in this case, we're not talking about, I mean, if it's objective, we're not, possibilities, different ways how the world could possibly be, it's not obvious that the rational response at all is that we average over. Because then it's not it's related to uncertainty and imprecision, not to different ways the world could be. That's one argument, and the question is, well, what's the actionable? I mean, what lesson to learn from this? There are actually climate scientists that say we should give up on or we should at least complement this with oh my God, what's it called? Storylines. Yeah. So instead of focusing on the spread, sort of pick some of the possibilities, potentially be informed. So basically, what they do is to say, this informs you about sort of the spread in some way. Now, perform an information-motivated sampling. So you're picking out particularly expressive cases, and then you do a case study. You really focus on the individual possibility and our response to it. And then of course the possibility also becomes a lot richer. So then it's about the various causal pathways, the local distribution of this, because this is like mean global temperature, right? So that's not very expressive about what happens in Brussels or in Stockholm. And instead you focus on this individually and you ask for these individual possibilities, what should we do if this happened? And then you still need to sample. This might be helpful, and you might want to go with the most extreme version, and you might go with the middle of the road version. But then you focus on these individual possibilities instead of saying this is all for the purpose of giving us a mean that our policy should then follow.
Yeah, okay, is that's the real purpose to get to a mean that then is going to be the guide for action, then indeed I see the problem. And I guess what one really wants is a combination of something epistemic and objective, right? Because in the end we think we can do different things, and so the world should be at least open in that respect, that there are objectively many possibilities. If we pollute more, then the world will be different than if we don't choose to pollute more, I guess. But there's also a lot of uncertainty that you want to measure, and those are different things, right? Yeah. And it's a bit crazy that it gives this. It's not always clear whether we are talking about objective or epistemic modality. Yeah.
I agree, and I think I think in this case, I think this is maybe also the case that people most balk at and go like, well, why exactly are we? What is the the relevance of possibilities. There's some more of insisting on this. There's some arguments that simply say you cannot interpret this as a sort of Bayesian model. And that's due to the fact that the nature of the individual GCMs is they're not independent of each other. So you have strong clustering. Some GCMs are very close together. There's some mavericks that are quite different, but nobody has ever tried to sort of do like to even attempt to say we are centrally organizing a distribution of different models. Right? So it's like it's voluntary. It's because it's high prestige and good visibility that some institutions put a lot of money into developing a GCM and then continuing it. But how this is done is entirely up to them. So they can go and say, well, there's this other group that does it this way, we do it exactly like this, except for this one assumption, and then they go off. Or they can say, we're going to start with a completely different structure. I mean, okay, within the limits of fluid dynamics, of course. But therefore we shouldn't treat these as individual independent attempts, each of which should have the same weight. And how to distribute the weight then is actually very difficult, right? Because what they did up to the fourth report is simply give to average over all the models with equal weight, and that was. But that's not a very strong argument for possibility. That's sort of like, it's almost like a negative argument. It's to say that we don't really see the reason why you're attributing sort of thinking of them as something like probabilities, or that they have equal probabilities as a uniform distribution. Instead, take a step back and only think of them as possibilities. I think of it more as a sort of like that we should think of these, if we think about these as objective possibilities, not epistemic possibilities, then there's actually an argument against using expected values as a synthesis and action guiding as anything action guiding, and then it also means that we should sort of engage with them in a very different way than as this is currently done. But there is, of course, the interesting broader aspect that, because this is something that's a look into the future. And in a way, I mean, as long as we have point predictions for whatever system, then it's plausible that that the target is the current system with its dispositions that will develop into the future. But as soon as we have uncertainty, or as soon as we sort of allow for multiple developments, it is ambiguous whether we're now talking about our uncertainty or about actual real sort of like objective divergence in objective possibilities. There's, I believe, but that might be because I'm not a climate scientist and that might be naive, but I believe that some of the tipping point features might be an interesting. So there's a lot of discussion about sort of what regularly the system will develop, and then there are these sort of more or less seen as more or less crazy potential things that could happen in the future. So one thing that I think is now rapidly moving into the mainstream is the question of permafrost and to what extent that can lead to either massive emission, but it could also lead to enormous growth in areas that were basically barren until now, and now those could be enormous carbon sinks. Another thing is the question of the Gulf Stream changes that can go in lots of different directions. Regarding affecting emissions, sort of concentration scenarios, and they are very difficult to treat, as far as I understand, as part of the dispositions of the current system. So typically we think of them as as switches that are switched in one direction, and then possibilities can open up downstream. And then we think of them as objective possibilities that need to be treated very differently from what we treat these things.
Cool. Thank you so much for the presentation. I very enjoyed it. Actually, it's a follow-up. Maybe you already answered this question. It's more of a general question. Is in scientific practice, yeah, is what your last answer. It's possible to distinguish all the time this epistemic and objective possibility, and you are telling us that could be hard to do that. And I was thinking, do you think that there is any possibility to go beyond this kind of dichotomy? I don't know, kind of a synthesis between the objective and subjective, concerning the fact that we are referring to scientific practice. So yeah.
Yeah. Yes. Very good and important question. So when I talk about epistemic possibility, I'm talking about a state of the actual world that is possible according to our current knowledge, right? So the judgment is about the actual world only. And the reference is to our current knowledge. Right? So the assessment is not happening by comparing it to the actual world or to the target, but to our corpus of knowledge. And then, as I mentioned, there are various problems here. So, like the kind of comparison that comes directly out of the most prominent definitions of epistemic possibility are kind of off, because it means that you are justifying a claim by saying that you're ignorant about something. That seems to be weird. But that's not the question. The point is that because epistemic possibility is about as I define it, is about the actual world, that contrasts it quite strongly with contrasts it strongly with objective possibilities, which are not about the actual world. Unless with the exception, of course, that the actual is also possible. Right? So there's the actual world, and then there are lots of non-actual possibilities besides it. Now, the way I use epistemic possibility is only focusing on the actual world, not the possibilities besides it. But of course, our relationship to objective possibilities is epistemically mediated. So it's not as if we in this way, every time we talk about objective possibility, we say, well, it's objectively possible according to our current knowledge. So in a way, it's a proper distinction works to say, well, there's the actual world, and then there are objective possibilities. That's on a you might say, if you're so inclined, on some sort of ontological or that sort of has a sort of metaphysical perspective, and then there's the question: how do we have access to something at all? And we sometimes use the term possibility to refer to the quality of our knowledge. So uncertainty in our knowledge sometimes is represented through the term epistemic possibility. That's the proper distinction, but it kind of gets a lot. I simplify it, maybe unduly. So in this way, there is we can nevertheless say that whether we're talking about the actual world and are uncertain about it, or whether we believe we're talking about a non-actual possibility about which we also might be uncertain. So properly saying, I'm talking about an objective possibility, and it's epistemically possible that this is objectively possible, something like that.
Yeah, but we cannot have all the objective possibility without the epistemic one, because
yes, that's right. But regardless, but what I'm talking about here is nevertheless distinct because that's epistemic possibility about the actual world. Yeah, that's the I simplified it because though that remains a contrast, and then I don't need to always say I'm talking about the epistemic possibility of an objective possibility, but I simplified it as if I were epistemically certain in talking about objective possibilities.
So, sorry, the last.
Please go.
I don't know if it's relevant, but then the epistemic possibility are all the time refer. Let me check. Refer to the future. Some projection that could be.
No, we are actually. It's an epistemic possibility that dinosaurs roared or something. Yeah. So.
Thank you so much.
Yes, thank you very much for your talk. I have a question, actually two questions. One is more general, and I think I'll start with this one. It's about the scope of this modeling, because it seems to me that the way you introduce it is that we have something modeled in our inferences. I was just thinking that in many studies which are targeted at studying actual world, we, for example, want to see the difference between two groups of patients, so I don't know, between organisms in two different environments, and someone who do statistical testing. And very often this involves that we have some null hypothesis, then we have some simple statistical model, then we have a conclusion that under this null hypothesis it's impossible to observe certain degree of difference between two groups, then we infer that probably the null hypothesis was wrong. And I was just thinking whether this kind of very basic statistical reasoning, which is very pervasive in science and in biology and everywhere, will it still be under the scope of this kind of modeling, or?
Yes, but it concerns in almost all cases we would think of the statistical possibilities as concerning epistemic uncertainty, right? So that's not made necessarily clear, but if you look at, you say, well, if you do null hypothesis if you do use simple sort of like significance level testing, then you are asking, then the probabilities you're checking. So if you calculate the p-value, is the probability of observing data more extreme than the actual observations you made. That's a possibility, right? You were sort of like, but it's not. It's actually it concerns only the question of how sure you are, right? I think so. It's rare that we're talking about objective. I mean, I don't know. I guess things really get messy when we talk about quantum physics. But otherwise, probabilities mainly deal with epistemic questions.
Yeah, I would agree that in the end it seems that
maybe not true because we could say when the frequencies are probability interpreted frequencies are not epistemic in that sense, right? No.
Yeah, because what I want to say that, for example, in genetics, when, for example, we have two genes and we're interested whether they are independently inherited or they are linked, we observe some distribution. And of course, there is epistemic uncertainty in the sense we don't know whether they are linked or not.
Mm-hmm.
But it's also, in a sense, the p-values we calculate, they also reflect just the frequencies we observe. And we may think that given that, for example, genes are independently linked, it still may have happened that we would have observed as if they were linked. So I'm not sure that it's in the end goes completely only to systemic uncertainties.
No, maybe not. Okay, so let's say that, in any way, I think that there are possibility considerations underlying all probability distributions, right? Because every probability distribution talks about, in one way or another, about a number of possible states, some of which might not be actualized, right? So, if you're a frequentist and you don't agree with that, then you say, no, they all have been actually realized. They actually are just the instances of that we have counted. So that's a way how to sort of say, well, in that case, you're only talking about the past and observed frequencies. When you're talking about, but there are of course other interpretations. So certainly when, for example, you talk about, if you want to talk about like propensities, so another you're thinking about probabilities attributed to often not to events but to objects, and those objects then have certain properties that are captured, like dispositions that are captured by this propensity to evolve into certain possible future states. And there I very much think that we're engaging in discussion on possibility and modal modeling. Because then we need to somehow get a grip on why we're thinking that certain possibilities are relevant and not others, and how to discern them and so on. But you said you had a second question. Maybe there was a follow-up on that?
No, it was not a follow-up.
Okay.
Is that follow-up?
Yeah.
Can I? So it seems to me that from this last question and answer, it's important to keep in mind that we do have we should separate the probability and the possibility, because it's not the same. Nonetheless, the way in which they relate for me is not so clear in general. Not for in general. I working on possibility. A lot of time I try to figure out how can we really distinguish the two in a
Now, how to distinguish probability and possibility?
Yeah. Generally speaking, of course, after that we can go into more philosophy and science and scientific practice stuff. But I don't know what is your.
Yeah. So I think that one answer is that actually comes out in relation to the climate models, in response to some of these claims that these are possibilities, to say, okay, what does it actually have? Why are we removing the probability from it? It simply seems to be just a step back, and it seems to be a very strong step back, sort of idea where you're basically saying no quantification. So then the simple idea would be to maybe say that probabilities are something like quantified possibilities. So that's the difference, and possibilities are just a weaker notion than probabilities. However, in this discussion then, so there's been there's this Australian philosopher has worked on, and right now I can't remember the name, I can look it up for you. He has proposed that maybe there are formal systems that try to develop sort of an axiomatization of quantifying possibilities in analogy to probabilities, but with different axioms. And there's if I don't remember the exact detail, but I think it's the independence axiom that is dropped in the possibility claim. And therefore, I think it's still strictly weaker, but you now have a quantification of possibility. But the claim is that it's different from probability. However, I'm not sure. I think we're losing out there. My impression is that we're losing a little bit the whole point of this sort of why do you have, I mean, how are we interpret, even if we can axiomatically distinguish it, we now have another quantification that makes it that nevertheless is distinct from the probabilities, but how I think the intuition boggles here, and we don't really know what we're measuring when we're quantifying possibilities instead. And then we begin to use that in a similar way, or as we use probabilities, or we're also aiming to somehow synthesize this into a single statistic, or it's a little bit. But I mean, if you're interested in that, I could provide you with I think there's in other cases I think it's much clearer, simply because we can't. If you think of this case, for example, it's clear that when we're talking about the possibility that life could have evolved in a different way, that here it's not clear how we would use a probability framework at all, right? It's much, because here we have so many issues with individuating, because we don't have really a common starting in the climate case. We have a common starting point, the current system, and how it might evolve. And we can say, sort of a number of different states they can evolve into, and other states they cannot evolve into. Those are the impossibilities, and there's a cone of possibility. And while within the cone of possibilities, we can now maybe give this state space within that cone that we can give different weights to. And then we end up with a probability on top of a possibility structure. But here, it's like, the state space seems enormous and entirely sort of out of our reach. So we wouldn't even. I have a hard time thinking of how we could possibly model this in a probabilistic way. And there I find it much more plausible to distinguish. No, here at best we can talk about possibilities and what is not possible, while probabilities that would be out of reach.
I can go through.
Peter, is that?
Okay. So it's a question precisely about this example, and the thing is, just now, I mean, it appeared to me very clear when you just presented it, but after that, I'm very much confused. What is model in this example? Like, I see the modal claim, which is produced that life would have evolved differently, but what is modeling practice like?
So I think the model here lies somewhere in this. The requirements needed to support Darwinian evolution. So you have sort of like an abstract, a general model of an organism that satisfies these conditions. So it can reproduce, there is mutation, it can maintain itself, those kinds of things, right? And then you're thinking of this organism as being containing X DNA instead of DNA.
Yeah. Okay.
But I think there are so synthetic biologists are on their way of trying to actually build such organisms. Therefore, I assume, they're no mathematical models, but there's something on paper, sort of where they stand at this point, and where they're trying to sort of actually put this together, and then it looks a little bit like Goddard's prototype, right? And then it's a model.
Peter?
That was probably follow-up. Yeah, follow-up. Sorry, that was super interesting. So, I was listening here, and could be the case that in that scenario we do have two kind of possibility. The first one is refer to the possibility to develop that model, namely to develop the molecule that we build in the computer simulation. And this is the possibility related to the model. And the second is the possibility claims that comes from the model. Kind of, okay, if this is possible, then the DNA is contingent.
Yeah.
Could be that here we have the difference between these two kind of claims, possibility, the model possibility and the possibility that follow is kind of, as you said, possibility claims. I don't know, it's really...
I think that I agree with that, and I hope I try to make that clear right in the beginning, where I say modal modeling concern scientific model or modeling practices used for the purpose of inferring modal claims. So it's really not about, I mean, the similar model structures can be used. So think of for example, the neighborhood. The neighborhood is those analytics sociology models. There, of course, the same structures are used to represent actual neighborhoods, right? But they can be used to also draw modal claims when suitably changed, right? They're not the same. They're not the same in the specific model, but they use the same structure. It's also on a grid, and maybe you sort of bend them so that they don't have borders or something. But it's not that the model itself is a possible or impossible structure, but it's the possibility claim that's derived from it, or the purpose of using the model for deriving such a possibility or generally modal claim that makes it a modal model. Yeah, it's important because otherwise also it can become very hermetic, right? I mean, if you're into math or computer programming, you can play around with mathematical structures, and you show that you can derive it's possible to derive following a result. Like it's possible to sort of arrive at the solution, or this has a solution, or it's possible to turn all blue fields into red fields with this rule in 10 steps or something, right? But exploring the possibility space within the model is something else, or within the formal structure is something else than using a model which already implies being some kind of epistemic artifact that in some ways is a surrogate for something, to derive modal claims that in some way are about the world outside of the computer or the formal structure itself. I think that's an important aspect.
Yeah, thank you.
Because otherwise everybody is just doing it. I mean, that's obviously what people, when you try to prove a formal result, you're trying to show a possibility, right? So that's or the other way around, when you do an impossibility theorem, that's
Peter?
Yeah, so my more general question, please, yes. So I myself very much in favor of seeing science in a modal way since quite a long time, and I want to test a bit how radical you are compared to me. So I like to look at science from a language point of view. So really look at what people say and how one could possibly think of formalizing that, instead of looking at the the formulas they just give or something and see that as their results, but really look like the full texts and the sort of language they use, and then thinking like, how can I really understand what they are saying? And then often, like, you just like read 5 sentences about any text in whatever science paper. There is a modal word with that as a logician I would model it modally involved there. It could be more to do towards the epistemic, but often you could like the intuition behind it seems to be at least quite objective modality, like especially if it's dispositions, they are everywhere. Probability talk is rarely epistemic. I mean, except if people really know about Bayesianism or something, then if they use...
You mean like it's not explicitly epistemic? Because as soon as you commit to Bayesianism, or...
Well, yeah, but so people who are, like, scientists who are aware of Bayesianism, they will clearly avoid objective talk. But those who are not and are just like using more intuitive notions of probability or statistics, it is very hard to read it charitably in an epistemic way. Because people have this idea, there's possibilities there's things that can happen, and once you think about it can happen, then that's nothing that has nothing to do with epistemic stuff, right? And then there's causality, which is for me a modal notion. But in general, the whole move towards experimental science, where we don't want to just observe the world, but want to do experiments in them, like do stuff with it, like push the world and see what happens. For me, that is like inherently modal concepts, because we don't care about what the world is. We care about what happens if we were to push it in some direction. That's why we do experiments. We set it up in such a way that we get the effect that we would in general achieve with such and such an action. And that's also what guides us in future in future actions. Now that we know what would happen if we did such a thing, we know that if we at some point actually do it, what would happen? So both the practice of science as an experimental thing and the language we use for it and the reason why we would want science, namely to guide our actions, all points towards a very modal reading of science, of about everything in science. Of course there is things where we just want to describe some better know some fact that happens, but often that is to serve in a broader context where we do want to achieve some modal knowledge. And of course, with Wiener-Kreis and so on, and other anti-metaphysical movements, we've become extremely wary of modal stuff.
Yeah.
But that should not be a good argument, right? We just need better formal tools to understand what we're actually doing, and don't imagine, because we're using modal language, that there's this modality should have some kind of religious or deeply metaphysical ground to it. It could just be the best way to describe the world in a very hardcore empiricist way, based on the data that comes to us and the fact that we want so. I don't want to make this too much about my own view, but I'm just wondering how far you are willing to go in this modal modeling, because the modeling aspect also for me seems also very important, because it's not always possible to do the real intervention. Interventions are difficult to set them up right, but if you have a model, then these interventions are the easiest things to do. If you have a computer model, you just change a variable and you see what comes out. If you have a small lake that represents a big lake, you can like do things in your small lake to see what would happen in the big lake. So the modeling aspect for all this interventionist notion of science seems very important. So it seems that, and so I'm wondering how far this view, it's like almost everything modal view, is separate from your view.
Right. Yeah. So thank you. It's nice to force me to reflect on this. I have sympathies for the view that you're sketching, but that's not my goal, or that's not my subject, put it that way. And the reason for that is that I'm interested in I'm less interested in the sort of overall understanding of what science is, and more interested in practice relevant recommendations. Mm-hmm. Because your view sounds radical, perhaps, or almost all things are modal view sounds radical, but could be countered by saying, well, yeah, fine. So, but we clearly have had great successes with our current modeling practices, and if you declare now that all this is modal, then so be it, right? So then our current modeling practices obviously work well. We might need to then sort of maybe adjust our language a little bit regarding what we mean by target, or sort of how this. While what I'm arguing is that no, actually there has been a focus on modeling as this model target diet, or maybe the model target purpose triad. But that by focusing on modal modeling, or maybe on particular kinds of sort of suitably constrained modal modeling that doesn't encompass everything, we see that those practices are not properly covered by the current account. And in fact, the recommendations that come from the standard account are not really applicable here. And therefore also things go wrong. And therefore, for example, one of the big issues we have is that currently nobody seems to really know how to deal with these agnosological strategies of coming up with another, but isn't this possible? Couldn't this possibly be the cause? Or, right? And so we seem to be quite defenseless about this at this point. Why is that? Why don't we have a notion of relevance here? Now maybe this lies somewhere else. That's sort of still very much the beginning, but it's so I don't want to concede that everything is modal, and therefore everything is already as it should be. Yeah, with regards to modeling practices. I'm saying that a lot is not modal. So we have engineers presenting models of a building where the building is actually there, and it's the model represents that existing concrete target in specific ways, and that guides whatever sort of intervention I now want to do. Or we have lots of targets lots of models that are representing abstract targets. So you might talk about models of organisms in some more general way, and that they're super important, but they nevertheless are about an abstraction of concrete actual targets on a sort of just certain features that are now represented. But then there are sort of some models and modeling practices that focus on something else, and because they want to get possibilities out of them. So one option is, and I've indicated that sort of in some of the literature that I pointed out to you, is to say, well, we need to push that. We need to somehow have this subsumed under the standard account. So it's all these models with their standard actual targets that nevertheless allow us to draw inferences about possibilities. And what I'm arguing in contrast is that I have no idea what targets you're talking about, and it seems to me that in these cases that's maybe metaphorical, but I don't understand, and more importantly, I don't get any kind of practical advice from it. I have no idea how I'm going to assess such claims in the light of such purported model target relationships. So it's about identifying that part and saying we don't have a good grasp of it, and we don't have a good way of giving epistemic and methodological recommendations, or epistemic judgments and methodological recommendations.
That's really interesting, and I was wondering, like, take that example of the building that's actually there. We have engineers have a model for it. So obviously, I mean, for me, it's obvious that gives us model information, namely information about what would happen if a storm would come, or what would happen if some damage was to.
Right.
That kind of model knowledge. But then there seems to be some kind of cases where we're more like scratching the surface of some new state space or something like that, of possibilities. A place where we don't know where we don't have such a nice model yet. Yeah. And they seem to require indeed very different tools. But is the modality here the real issue? I mean, first I should ask, is it true that there is modal information in the model of the building? Because you seem to first say no.
No, what I said was that in the model of the actual building,
Mm-hmm.
the model is a model of an actual target.
Yeah.
So, but I agree that we can draw some model inferences from that. And I would argue, I find the explanation attractive here that certain dispositions are clearly represented by this model, right? So that if you put stress on the model in a certain way, and you're using some scaling up, then you will see why instabilities occur, be that wind or something like that. And those are dispositions that we can clearly identify or sort of attribute to the concrete target, right? And that's why there's some model inferences that the model of the actual target allows us. While in other cases, it seems that we are aiming for modal inferences that we cannot get from so clearly identifiable dispositions attributed to a particular target, or even to a generalized target. We just don't. I mean, I think the XDNA case, or even the climate tipping point aspects. Those were moments where you say, okay, so no idea what sort of target that would actually be. Well, how should we set the target? And even if we were able to then set the target, then we can't. We don't have a handle to actually assess that. So then we have clarified conceptually what's the relation. And it doesn't give us still no standard for assessing the accuracy. Mm-hmm. While in the model, you can put the model in the wind tunnel, and then you need to adjust because aerodynamic properties are actually scale dependent, so you need to scale them up. But people know how to do that, so you can use the model to identify. Disposition. It's some of the dispositions of its target, and that will be a way to say, yeah. So, are you unsure about this? Well, then go and actually perform wind tunnel experiments with parts of the building or something, or parts of the vehicle, right? Instead of just the model of it, and then you can compare it, and then you validate the model about even these dispositions. While in many of the cases that I'm interested in, you can't. Yeah. But I agree. I mean, in this way, I realize that that I need to. I've now admitted that that I, on the one hand, identify modal modeling through the intention of inferring modal claims with the help of models, and I've admitted that some of these models are some of these modal models might nevertheless have actual targets, and might be really, you know. So, and then this might sort of undermine the generality of this claim at this to that degree, right? We have some. I need to find a finer grained individuation. You know? So. I'd have to at least at this point sort of use an ad hoc modification. Some MM should be treated separately, and that's not an empty set. But some of the currently characterized modeling might well at least not distinguish itself in terms of the model target's accessibility.
Yeah, really. I think it's a good time to thank our speaker.
Mm-hmm.